So we have one more modern model of the atom left to add to our worksheet notes that you're adding to. And we have gone from the Greeks all the way to John Dalton's modern atomic theory, to J.J. Thomson's cathode ray experiment, who discovered the electron, to Ernest Rutherford's gold foil experiment, where he discovered the nucleus of the atom, to Bohr, who quantized the atom into certain discrete energy shells based on electrons going in orbits. And now we're going to go with the final model. Now let's go back a little bit with Bohr, because I want you to add something to Bohr. Now, in Bohr's model, he had the nucleus, and of course he had these these orbits, that kind of like planetary model of orbits, where electrons were in these distinct energy levels. And these electrons, of course, to go from one position to another, needed distinct energy. And we call this n equals 1, n equals 2. We said this is called the first principal energy level, the second. We also call them shells of electrons, all good words you need to understand. Now, the problem with Bohr's model, and before I get to the problem, there's so much greatness here. Niels Bohr was a rock star when he made this atom, and he won a Nobel Prize for quantizing the atom. He was the first one to take matter and quantize it, and he was based on how the electrons were arranged. He was the first to talk that electrons had discrete energy levels. They go to and from to either absorb energy, to absorb energy or release energy. Now, all of that is still true today. None of that has been taken back or said it was wrong. But the problem with his model is that he was only able to explain the red spectral lines and the green spectral line because he was dealing with a one electron system. So only the one electron system and one proton system, currently he can only explain the spectral lines of hydrogen. So that was the issue. So his limitation, as you should put, his limitation, not in the current model but in the Bohr model, was he can only explain the what? The spectral lines of hydrogen. Now, if you remember, the spectral lines of hydrogen, where you have the third energy level. We had the fourth, and I think we had the fifth, and we had the sixth energy level. I'm just drawing parts of it. And what you noticed was, in the third energy level, this is n equals 3, electron jumped from the 3 to the 2, it went red. From the 4 to the 2, it went green. From the 5 to the 2, it went a blue color. And from the longest leap, and most energy, largest of the energy of the photons here, we had that violet color. So everything we talked about is still true. But this only worked with hydrogen. Only. Okay, he could not explain the energy changes in the emission or absorption spectra of other elements. Now why? Well, I'll give you one example why. One of the reasons why is that when electrons go in circular orbits, they need energy. Another way to explain it is, well, if you have a charged particle moving, we know it gives off electromagnetic radiation if it was moving. Okay, and that's why atoms that move in our body give off thermal radiation. But the point being is, and no point intended, is that electrons, if they move, they're going to give off energy if they're charged. We know this. So if you're giving off energy, that means the electron's going to lose energy and it's going to eventually slam into the nucleus. And that doesn't happen. So he needed we needed to change the model. Well, the modern model did this. Okay. Now there's a lot of important work that occurred. De Broglie and Schrodinger and Niels Bohr himself was a champion for the movement of quantum mechanics. But what you have to know, I'll just wipe this out. What you have to know is the following. Number one, the modern model discovered that electrons aren't particles, as Bohr said. Okay? Electrons actually exist as waves or have large wave properties. Now there are particles, but they actually have a lot of wave properties. So we say that electrons in the modern model can behave with both wave and particle-like properties. So that's important. So the first thing you want to write down in this new section is, in the modern model of the atom, electrons can exhibit or have wave properties, wave and particle properties. Now, particle properties means they can exist as a point charge, as a piece of matter. Wave and particle properties. That's important. So the key here is that electrons in the atom, okay, exhibit a lot of wave properties, meaning they're like a wave, like light. And we call this a duality of nature, okay, because they can exist as a wave, like a light particle, like electromagnetic radiation, and they can exist as a particle. And if I got into more quantum mechanics, you'd understand this wave-particle duality, okay? But it's important here they have both properties. Number two, because electrons are existing as waves, where they are in their region of space they exist has to be based on probability. We can't say with definite confidence exactly where one electron is because we're not going to treat it as a point. We're treating it as a wave. And where is that wave? Well, it's spread out. So probability is what we use to describe where electrons are. Okay, we can't say they're definitely here or here. We can only say with some probability. So the modern model of the atom uses probability. And third is that the region of space that these electrons actually exist, regions of space for electrons, has a particular name that you have to know. It's called an orbital. Notice the name, guys. It's a lot like what Bohr said. It's like an orbit. Wait a minute. Why are they using the word orbit in here if we found that electrons do not go in circular orbits? Why are we using the word? Because it's important to give respect to Niels Bohr, because even though they don't move in circular orbits, everything else he said was right. There are specific energies. Electrons, when they move from one energy level to the other, could be either absorbing energy or releasing. So everything he said was right. He just had parts of his model incorrect. So to give Niels Bohr due credit, they kept the word orbit and added tull. But you understand, this is a region of space where two pairs of electrons can exist. Okay, so these are the key indicators when you know you're dealing with the modern model. They're going to ask you about what kind of properties do electrons have, and they have wave and particle properties. They're based on probability of where they're found, and where they actually exist is not an orbit but an orbital. And I'm going to show you some pictures of those in a second. Now, the modern model of the atom actually has a couple of other different ways we can call them. So I'm going to write them here. So the modern model could be called the Electron Cloud model. So Electron Cloud model is another way you could hear this described. Another one is a quantum mechanical, or quantum mechanics is the math used to describe electrons in this new model. So quantum mechanics, or sometimes the mechanical model. All right, so quantum mechanics, all right, and probably that's really all you're going to need. So the electron cloud model, the quantum mechanical model, it's all the current model of the atom. Now, what does this electron cloud business really mean? Well, if you look here, okay, electron cloud model is given that name because if you consider the atom, instead of the Bohr model, okay, as I'll write under here because I don't want you to write that, you're going to draw this in that little box that you have. And let's put a positive for the nucleus. That's not changing. Protons and neutrons are in the nucleus. Of course, the nuclear charge in the nucleus is due to the protons. And what we're going to have is we're going to have in the first major principal energy level, electrons exist in a region of space called an orbital. Now, I'm not drawing dots to show each electron. I'm showing dots where the electrons could be based on probability. So I am drawing an electron cloud. That cloud is showing the possibility where electrons can be. Again, we don't know exactly where they are because it's a wave. It's based on probability. So the first n equals 1 represents this region. This region, which is really a standing wave. It's a wave, right? Electrons exist as waves, okay, is where the electron is found based on probability. Is it here or here? Don't know, but we know with probability it's somewhere within this region. And this region is called, again, an orbital. So in n equals 1, electrons exist in this sphere. Interesting enough, the distance that we calculate for the radius or diameter of the sphere matches up exactly with Bohr's first energy level. So although he said it was in circular orbits, okay, we now know that the most probable position for an electron is probably right on this edge. It could be anywhere inside the sphere, but the most probable location is somewhere on this edge here, which matches up to Bohr's circle, except of course our electrons can be anywhere and there's some kind of wave function or wave that's standing in here, that's in this region. Okay, so that's n equals 1. Now, given another color, let's do, I don't know, let's be crazy and go with, let's go black. All right, now the black, or the next region, n equals 2, would be just like Bohr said, existing farther away, but because we're talking about the electron cloud model, we would say that those electrons can exist anywhere in this bigger sphere. This bigger sphere encapsulates the smaller sphere. So I'm drawing another cloud, but this cloud is bigger. And the next energy level starts with an S region or S orbital. This S orbital, I'm drawing that to black, I'm not trying to black everything out, but if you can think about this, this is exactly this entire region in this circle is what I'm drawing here. And that would be n equals 2 region. Notice it encapsulates, what that means is the other region is inside. So this one's farther away, just like Bohr said. So if an electron, and let's make that, I don't know, yellow. So if an electron is somewhere here, for it to gain energy, it goes to a higher energy level, it goes farther away from the nucleus, which we now know is less stable. So everything he said is right, except electrons don't exist in these orbits, but in these very, very cool little standing wave functions. Okay, so the key indicators here are the modern model, electron cloud model, quantum mechanical model. Okay, now mechanics is a mathematics that deals with waves, but the key here is electrons can both exhibit wave and particle properties. It's based on probability. The dots I'm drawing are showing these probability, and the region of space where you call this actual cloud is called an orbital, where 2 electrons can exist. Okay, and that's what you have to write. You should write those 3 things. You should have this drawing, and that'd be good enough, and of course I'll collect that. But I want to show you now what these regions of space called orbitals actually look like as we get beyond n equals 1. So hold on to your horses there for a second. And let's hit the 1s. Now the S represents a sphere. Now this sphere represents an electron cloud of possibilities of where electrons. Is electron here? No, it's here. It's all over. It's a wave. It's not a particle. And that wave exists all here. However, the most probable location of that wave, okay, however you want to think about it, is toward the edge, but it can exist anywhere in this circle. Of course, in the middle. The X, Y, and Z represent just different planes of dimensions. Z is up and down, and these are different directions. Now the 2s, this would be n equals 2. All right, and n equals 2, all right, you notice that I encapsulate, notice this got bigger. So an n equals 2 electron, okay, has an s orbital. Now you don't have to know about the s orbit, it's spherical. Electrons can exist anywhere in this, okay? And then there's another orbital that's a dumbbell. It's even farther away. You don't have to know these, but these are different than the circular orbits. But what do we know? This is higher energy. It's farther away. It's a 2. In the second energy level, there's 2 types of orbitals. You don't have to know that. But again, the shape of these orbitals is due to the 3-dimensional wave that electrons make. Now, let's go to the 3s. This is when n equals 3. Notice the circle again. Encapsulates everything. So everything in the 3s, or everything I should say in the third energy level, n equals 3, is on average farther away than the others. So what I'm showing you here is the actual shape of the orbitals And these represent the electron clouds. You're not responsible for them, but I'm showing you so that you get an idea that this isn't as clear cut, and it's not Bohr the Bohr diagram is the end all be all here. There's more to the story. And again, you're responsible for knowing that this is the quantum mechanical model where electrons exist in these shapes called orbitals, all right? And they're based on probability of where they're found, which is really based on the proximity of the nucleus too, and which is what their energy level is based upon. And of course, the region of space is called the orbital. Okay? Hope that helped.